Amrut Mahotsav.
Okay, please go ahead. Please go
Yes.
ahead.
Yeah. This session is part of our Azadi Ka Amrut Mahotsav. Azadi Ka Amrut Mahotsav is an initiative of the Government of India to celebrate and commemorate 75 years of progressive and the glorious history of its people, culture, and achievements in India. This Mahotsav or festival is dedicated to the people of India who have not only been instrumental in bringing India thus far in its evolutionary journey, but also hold within them the power and potential to enable Prime Minister Modi's vision of activating India 2.0 fueled by the spirit of Atmanirbhar Bharat. Azadi Ka Amrut Mahotsav is an embodiment of all that is progressive about India's socio-cultural, political and economic identity. The official journey of Azadi Ka Amrut Mahotsav commences on 12th March 2021 and it starts a 75-week countdown to our 75th anniversary of independence and will end post a year on 15th August 2023. Thank you very much. Now, may I request our Professor and Chairman, Professor Amresh Chakrabarty, to introduce the guest and the CPDMCEFC Smart Factory. Thank you very much, Professor.
Okay, thank you, Dr. Srinivas, for the introduction. Well, I need to introduce two things. So first, I'll start with the Center for Product Design and Manufacturing and the CFC, which jointly organizes this webinar series. Center for Product Design and Manufacturing is one of the 40 plus departments at Indian Institute of Science, which is, I suppose, the highest ranked university in India. And we champion the design and the manufacturing aspects of the portfolio of the university. CFC stands for Common Engineering Facilities Center, which is a center of excellence established by the Department of Heavy Industries, Government of India, for creating a demonstrator smart factory platform, as well as championing research, innovation, teaching, awareness, and other programs around it. So this webinar series is basically a joint series among the two. Now coming to my dear friend and colleague, Professor Yasushi Umeda. Professor Umeda, I know him from, I think, 1998, when I was in Cambridge University and Professor Umeda was attending, he may not remember, the IFIP WG 5.2 CAD series with David Holden, who was organizing it there. And I was taking notes of the conference as a PhD student. So it was a great learning. The biggest learning that I had was that I couldn't understand anything what was going on. And that shows that you need to have in-depth knowledge in an area in order to make sense of international conferences that are the cutting edge of knowledge. So that was a great learning for me. But then we became colleagues. I managed the Cambridge Tokyo University partnership for research for about 10 years when Panasonic actually funded the project, and I frequently visited Japan and became greatly impressed by the country and the people, and of course came to know Professor Umeda in great deal of closeness. So he has been in the University of Tokyo, did his PhD under Professor Hiroyuki Yoshikawa, who is the pioneer of design, modern design research in Japan, and at the Precision Machinery Engineering at University of Tokyo. And then I think Professor Umeda has been in multiple universities, Tokyo Metropolitan University, if I remember correctly, and then also Osaka University before getting back to his alma mater as a professor. And this RES, the Research into Artifact Center for Engineering, was the equivalent of the Engineering Design Center at Cambridge, and therefore were a common partner in carrying out design research together. One major area of research, two major areas of research that Professor Umeda has are both very important. One is functional modeling, modeling of functions, and also sustainable engineering. So he has been, of course, prolific in his publications: 29 books, 150 plus peer-reviewed articles, 19 patents, and so on. 5 of his papers won Best Paper Awards in various journals and conferences. And as you can see, lately he has been interested in smart manufacturing systems, life cycle engineering, design, sustainability science, etc. have been his passions in the past. And I suppose smart manufacturing actually encapsulates all of them in the same now basket. So development and implementation of the concept of digital triplet is, I suppose, going to be a major focus of this talk. And I am looking forward to listening from him. So I warmly welcome Professor Umeda to deliver his talk.
Okay, thank you very much, Amaresh. Very warm and long introduction. Thank you very much. I'm quite happy today. So let me show my slide first. Can you see? Okay.
Yes, I can see and I can hear. Please go ahead.
Okay. I'm quite happy today since I can meet Amaresh, although it is online, but I'm happy to see your face. Okay, let me start my. Thank you very much for giving me make a lecture on digital triplet of learning factory enhancing engineering activities in smart manufacturing. Let me change the pointer. Okay, and okay, as Amaresh introduced, I'm an old friend of Amaresh, Professor Amaresh Chakrabarty, and my research interests consist of 3 areas: sustainability, including eco-design, product lifecycle design, product lifecycle engineering, and the second one is next generation manufacturing system. And the third one is design theory, including function modeling, as Amaresh introduced, and maintenance engineering. Today, among them, I focus on the second topic, next generation manufacturing systems. Okay, before going to the main topic, let me introduce the research center I belong to, which is called RACE, as Amaresh said, Research into Artifacts Center for Engineering. A little bit strange name, but this is the official name of our center. And
Professor?
Yes?
Apologies. Maybe you can switch off the video so that voice can be more clear.
Okay, let me stop the video. Okay?
Yeah.
How about it?
Yeah, no, it's much better. The audio is much better.
Oh,
yeah.
Thank you very much. Okay, and what did I say? Oh, okay. And as Amaresh said, the center has a collaboration relationship with Cambridge Engineering Design Center, and my center is reorganized in 2019, and the main focus of is set to draw future visions of manufacturing and to develop system-oriented technologies for realizing the visions. The center consists of 3 divisions: Value Creation Division, Cognitive Mechanisms Division, and Applied Intelligence Division. And I'm leading the Value Creation Division, and this presentation introduces you the overview of the research of this division. Okay. My presentation consists of 4 parts as shown here, if the time is permits. First, I'll summarize the megatrends of manufacturing. All of you may have known it. Second, by comparing with the trends, I'll describe features and issues of Japanese manufacturing industry. since I guess the situation of manufacturing industry in India is very different from that in Japan, you will find something by comparing Indian situation with Japanese situation. Third, I will introduce our concept digital triplet. It is a trial to incorporate human knowledge and intelligence into digitalized manufacturing systems. And fourth, I'll illustrate a learning factory we are developing at RACE. So let me move on the first part, megatrend of manufacturing. Although most of you may have known, let me summarize. The first trend is digitalization or digital transformation of manufacturing, such as Industry 4.0, all of you have known, Industry Internet. Digital transformation in manufacturing industry is the key for competitiveness. That's obvious. And second mega trend is sustainability, including SDGs, Sustainable Development Goals, Paris Agreement for carbon neutral, and circular economy for circular usage of resources. So incorporating sustainability into the main activities is indispensable nowadays for any companies, and to produce innovation in relation with sustainability is the key. In this context, I believe that manufacturing industry should transform into life cycle industry, which supports all activities throughout product life cycle, including purchasing, manufacturing, operation, maintenance, upgrading, and end of life. The trend from supply side include supremacy of platformers like GAFA. Shall we become a platform or not? And can we become a platformer? That's the problem. That's the question. And if we stay in the position of a manufacturing company, the question is how to cope with the platformers. So fourth trend is emergence of mega manufacturers in emerging countries like Samsung, Honghai, TSMC in Taiwan. For Japanese manufacturers, it seems impossible to defeat them in terms of mass production. That's a problem. On the other hand, the trends from demand side include changes of people's sense of value, including sharing economy, internet auction of second-hand goods. So nowadays, ownership product is not so important. Value proposition by product service systems, rather than just selling product, is important. And we can see the progress of mass customization, including co-creation and user-led product development. Finally, Asian market, including India, China, and Southeast Asia. This is very huge emerging market, and it seems that people in the market want cheap products, so to speak, with moderate quality. Among others, this presentation mainly focus on the digital transformation in manufacturing. On this issue, Professor Takahiro Fujimoto, who is a famous economist in Japan, just in Japan, gave an interesting interpretation as shown here. He draws this figure consisting of high altitude of sky and low altitude and ground. High altitude is the world of the pure ICT, where platformers like GAFA flourish. And ground is the world of pure manufacturing. Mega manufacturers like TSMC, Honghai, Samsung are very strong in this world. And between these two areas, low altitude is emerging, where ICT and manufacturing are mixed as an improvement. exemplified by Industry 4.0. Siemens, IBM, GE are very strong in this world, but there might be some chance for Japanese manufacturers, perhaps also for Indian manufacturers, because you are very strong in software. Here is the focus of this lecture. So let me summarize the features of Industry 4.0. This is industrial revolution that connect factories and all supply chains by ICT, IoT and ICT, as shown here. And this will result in smart manufacturing, like machine-to-machine negotiation. This will improve the productivity revolutionary and enables massive mass customization. The original concept is sometimes criticized that such automation may steal jobs of workers. But nowadays, the concept of Industry 4.0 is expanded to include human-centric and sustainability. I think the essence is cyber-physical systems, which is a system where cyber world and the physical world are deeply connected. Information is acquired from the physical world, processed by the cyber world, and the physical world is controlled by the cyber world. Okay, physical world is okay. So digital twin is also an important concept. Digital twin, my interpretation is digital twin is a form of CPS, cyber physical systems, and the model in the cyber world corresponds to the object in the physical world one by one. So typical usage is at the design stage of a manufacturing system. A superior engineer determines conditions by simulating various situations in the cyber world, and if he or she finds out a best solution, he or she implement it in the physical world. As I said, Siemens takes advantage in this domain, low altitude of the sky. Let me show you a demonstration video by Siemens. I hope you have not seen it before. Can you hear the sound?
Of the future, both the work
Yes, we can hear.
Okay.
They will be completely networked and control production autonomously, and in a way that is more efficient and uses fewer resources than ever before. The possibilities are so vast and groundbreaking that many experts refer to it as a fourth industrial revolution, Industry 4.0. The first steps towards Industry 4.0 have already become reality. It all starts when mass production components become a unique item, with their purpose predefined at the outset. Because even before manufacturing, the component exists in virtual reality, including all information required for its production. But all the other necessary components also have to be mapped into the virtual world. They also get names and addresses, and thus an identity, so that they know where and when they are needed in the production line or process. Equipped in this way, they are able to negotiate their way through the digital factory for kilometers before reaching their destination. Arriving at the processing station, the workpiece is identified and the machine calls up in real time all information needed for processing. After each station, the work gets checked automatically, either optically or by using other measurements. Deviations from target specifications can thereby be discovered on the spot, and faults can be eliminated quickly. If a machine needs replenishment or maintenance, it issues an appropriate request before shortages or breakdowns are experienced. The amount of resources used is immediately recorded in the system, and stocks get updated. During processing, all relevant data for the product is stored in its own digital product memory. This means that every stage of production can be traced precisely. In the factory of the future, machines and workpieces will even communicate directly with each other and make autonomous decisions about the next production step, comprising a system that is decentralized, efficient, and flexible. For this, so-called cyber-physical systems are the key enabling technology. But for all this technology, humans are still crucial. Even in a highly automated production environment, creativity, experience, and the ability to assess and evaluate situations remain irreplaceable. But technology can provide valuable support. Operator-safe control systems already allow automatic and manual production to be combined. And regarding quality control, employees use augmented reality to determine whether the product meets the required quality standard and can be shipped to the customer. Electronics and software allow for ever higher levels of networking to be reached. Completely new, complex systems are being developed in next to no time. The German electronics industry is at the heart of this rapid change with its own innovative products. Some important questions need to be resolved before factories become truly smart, including topics such as standardization and IT security. Yet the opportunities provided by Industry 4.0 are enormous. Productivity can be increased by up to 30%, and both the quality and diversity of products will significantly rise. At the same time, the period between development and production will shorten. Thus, Industry 4.0 will make a decisive contribution towards maintaining and improving Germany's competitiveness as an industrial location center.
Okay, this is a typical image. You may have known image of Industry 4.0 based factory. By the way, I forgot to tell you, but you can interrupt me at any time if you have any questions or comments on my that topic. Okay. Oh, sorry. Okay, and for example, German manufacturing companies are very active in proposing the concept of next generation manufacturing systems. Not only Siemens, but for example, KUKA, German robot manufacturer, proposes like this matrix production for achieving very high flexibility. As shown in this figure, there is no production line. I can show you, I hope I can show you something. Let me see. Just a moment. Just a moment. Okay. And what happens with me? Okay. You can see. Okay. Let me go back. Sorry. Just a moment. Let me go back. I cannot go back. Go back.
Yes, you're back.
Okay.
Mr. You're back.
Can you see? What can you see? Just a moment. Sorry. It's very difficult to operate. Okay. I think I'm now fine. Okay.
Matrix production by KUKA.
Yeah. Okay. And there are several demonstrations videos in the internet using very cellular flex manufacturing system of AGV by 5G telecommunication. So, okay, this is a very rough summary of Meltran. And shall we move on to the second part? I think you don't have any questions. If you have any questions, I'll accept them. Okay, fine. Okay, so let's move on to...
The mics are open. If anyone would like to ask any question, they may raise their hand. Thank you.
Okay. Does somebody have any questions? Okay. Okay, so shall we move on to the features and issues of Japanese manufacturing industry?
Sure, thank you.
Okay. Oh, sorry. I'm a mistake about it. But you may know Toyota or Suzuki or Honda. I think Suzuki is very famous in India. Sony, Panasonic, and so on. Historically speaking, I have to say, it was said Japan as number one in manufacturing in 1980s. At that time, Japanese manufacturers exported quite a lot of automobiles, TV sets, motorbikes, and other home appliances to US and all over the world, and caused trade friction with the United States. Oh, sorry. You may have known four steps of industry revolutions. The first step is steam engine. The second is mass production for the production system. And third is automation, including CAD, CNC, and industry robots. And fourth is now. And Japan was strong in the era of Industry 3.0 here. So let me discuss features and issues of Japanese manufacturing industry, mainly issues in the mega trend we discussed. So first, about the digital transformation. Japanese manufacturing industry failed to propose a new manufacturing paradigm from 1980s until now. Because Japanese manufacturers are advanced in Industry 3.0, as I said. In a factory, machines and automation Machines are automated and everything is digitalized, but not connected to outside. And especially each company automated in their own way without employing standards, platforms, or standardized tool like Siemens and subsystem. And there are very thick barriers between companies. Very thick barriers between companies hinder being connected. Second, about the sustainability, I have to say that the attitude towards sustainability is very passive and just follows the legislation. This is not adequate nowadays, and they have very weak motivation to create innovation in relation with sustainability. And about supremacy of platformers, I cannot imagine world's platformers like GAFA come out from Japan. If so, the question is part supplier to the platformers a good position for Japanese manufacturing industry? I don't think this position is sustainable, I have to say. And emergence of mega manufacturers in emerging countries. Japanese manufacturers was very strong in 1980s, as I said, and failed in the mass production competition after that, around the year of 2000. But still, they are reluctant to make revolutionary change. That's a problem. And change of people's sense of value. Japanese manufacturers persist in producing high-quality hardware and not good at planning service business. And finally, Asian market. Let's assume that this phrase is true. People in the market, in this market, want cheap products with moderate quality. So Japanese manufacturers are not good at making such product. And when we visit Southeast Asia, it is often said that something is very cool, but Japanese products are reliable but not attractive. So this is a kind of position of Japanese manufacturers in the Asia. So let's go back to the issue of digital transformation. A typical behavior of Japanese manufacturing is here. They go on in their own way, without employing standards. On the other hand, German team considers standardization is very important. For example, this figure indicates, I think you have known, RAM 4.0, reference architecture model industry 4.0. Why standardization is so important? We can interpret that industry 4.0 try to transfer manufacturing systems from know-how based, which Japanese manufacturers are good at, to modular and standardized one. In Industry 4.0 aim at high-level automation for cost reduction in the first sense, but digital transformation and networking is for flexibility and mass customization. In other words, the concept of manufacturing system is based on digital, modular, and architecture, which requires top-down thinking. And I think this is almost correct approach to the next generation manufacturing systems. But Japanese manufacturers are not good at these three items. That's a problem. My personal observation on Japanese manufacturing industry is as follows. They have too large legacy to act quickly and prefer status quo. to jumping into the digital manufacturing. For example, they hesitate to invest for transforming to the digitalized manufacturing and trying to high quality hardware products because they cannot escape from the past successful experience in 1980s, namely mass production of high quality products with low costs.
Professor, may I ask a question here?
Yep.
Japan had a successful Kiretsu system, right? Where enterprises sort of grouped together, and there was say in the second half 20th century, if you look at it, it was more about this series of companies working together and like informal business group and releasing the products. Each entity proud of its own outcome, and it was like almost like personal prestige for each company and person involved. Can that same Kiretsu be kind of converted into Industry 4.0 basis?
I don't think so, because such industry, this is just my assumption, but such group of companies, as you said, is rather vertical. Do you understand them? Okay.
Yeah.
And I think Industry 4.0 assumes more flat and networking ecosystem through the internet. Many companies can join that network, but so very open-ended or open-minded, and but Japanese the corporate groups, the traditional one, is very how can I say, very conservative, or how can I, very strong, but not open-minded.
Okay, understood.
Okay. Do you understand my?
Yes.
Okay. So let me continue. Where was? Okay. So on the other hand, they keep pride of high quality producing high quality products, or they have very high motivated, high skilled workers, and they have very strong mind of my company's original way of manufacturing. So let me show you a typical example of digitalization in Japanese manufacturers very quickly. Typical pattern of SMEs manufacturers is like this. They added IoT capability to machine tools since the government gives some subsidy, and they can collect a lot of log data of machine tools. But they do not know how to utilize the data for creating value. That's a problem. Machine tools manufacturers provide, for example, preventive maintenance service, but SMEs hesitate to provide their operation data to the manufacturers. On the other hand, of course, some manufacturers try to win an advantage in this area, include FANUC field systems and Mitsubishi Electric Edge Cross. They want to be platformers in digital manufacturing. But these two frameworks are just platforms of IoT, connection, not supporting kind of contents, so to speak. Let me click. Sorry, it is very troublesome, but let me show. This is kind of a field system video, very short one.
Field System is an edge-heavy open platform which connects, monitors, thinks, and drives all machines and devices on the factory floor. It connects machines and devices at the edge, regardless of the manufacturer or generation. Through networks which work with Link-I or through a vast range of applications, it monitors and performs preventive maintenance. Fanuc's AI uses Field System or the Link-I series to gather and analyze data which is suitable for artificial intelligence. The intelligent usage of machines leads to a smart factory which is highly efficient and optimized.
Something like this. Let me see what happens. Sorry. Going back. This one. And what happens? Very complicated procedure. Okay. And I hope you know the company name Hitachi. Hitachi has a kind of Umeda. It's a digital data analysis platform, and they say that they started DX as a service, as a new service, digital transformation as a service by utilizing Umeda. Umeda is kind of a very big data analytics platform. Okay. So I can point out two problems from my standpoint. First, the Industry 4.0 type digital transformation in manufacturing might not fit the strengths of Japanese manufacturing industry. The question is, what is the strengths of Japanese manufacturing industry? I asked to the young manufacturing engineers who are hope of the future in a famous Japanese manufacturer. The answers, there are a bunch of answers, but some typical answers include keep promises, even if they are verbal promises, not written, or collaboration among different sections. Well, read, this is, I think, interesting. Read what is not written in the drawings and complement their defect, assuming the what is not written. Or even if the design not good, the manufacturing section produces products by complementing it during the startup production stage. I don't know this is good thing or not. And continuous improvement named Kaizen. Okay, so perhaps the strength is continuous pursuing high quality in manufacturing, which result in high quality products and continuous improvement in production. This is first problem. And the second problem is many engineers and technicians cannot follow the digital transformation. However, in the digitalized manufacturing systems, they should execute engineering activities, including planning, design, development, construction, operation, maintenance, Kaizen, continuous improvement, and replacement of manufacturing systems by utilizing the cyber world in addition to the physical world. But they are not prepared. Perhaps we need to new manufacturing strategies after mass production of high quality products. So for the first topic, we should transplant the strengths of the Japanese manufacturing industry to the new vessel, I mean, digital transformation. So very human-oriented. And for the issue 2, we need new education curriculum for manufacturing system engineers. The current curriculum for manufacturing engineers in Japanese universities, for example, in my university, is very old-fashioned. We need not only manufacturing science and technologies, but also IoT, CPS, and AI, and we need some system thinking. In this presentation, I cannot touch upon the second issue because of the limited time. The focus this presentation is manufacturing system engineers, of which role model is as follows. In a typical Japanese manufacturing company, they are the main intelligent workforce for conducting various engineering activities, including design of manufacturing systems, or operation and maintenance of manufacturing systems. And they are always stationed at the shop floor and continuously improve the manufacturing systems with workers. So next, let us move on the third part, digital triplet. Do you have any questions or comments on the second part? Is it fine for you?
Yeah, I think so far so good. Looks fine.
Okay. So let's move on. So digital triplet, we are proposing the concept of digital triplet as a form of cyber physical production system. We observe that Industry 4.0 takes a rather top-down approach, assuming CPPS or cyber physical production system do not change frequently since they have enough margins and robustness. It aims at automation as much as possible, and perhaps it is not assumed that CPPS is modified by workers at the manufacturing site. But as we discussed in the previous slide, the strengths of Japanese manufacturers include field experts' diligence, knowledge, and skills, everyday Kaizen. As a result, the production lines are kept improved under the lean concept. If so, CPPS should also be kept improved by the manufacturing system engineers' initiatives. For this purpose, digital triplet aims to support engineers to solve problems and to create various values throughout a product life cycle by encouraging these strengths rather than just pursuing automation. The image of digital triplet looks like this very not beautiful picture, but while CPS or digital twin consists of the physical world and cyber world, digital triplet consists of physical world, cyber world, and intelligent activity world, where engineers works so as to create values by utilizing human knowledge and digital twin. Digital triplet integrates these three worlds to realize integrated support of engineering activities throughout the product life cycle, including design, manufacturing, use, maintenance, and so on, and circulation of resources, very important. Let me illustrate an engineering activity on digital triplet. From now on, engineers should execute engineering activities mainly with the cyber world in addition to the physical world. In such a case, an engineer executes an engineering activity, and the activity consists of data collection, information analysis using AI tools, some simulators or CAEs, other tools, and evaluate the result and make a decision. And if needed, execute a plan. We call this cycle engineering cycle. When an engineer executes this cycle, cycle creates some value from the data. These round rectangles are modeled in the traditional CPPS by Siemens, so to speak. But we'd like to let the manufacturing system engineers construct such engineering cycles in daily work. This is a kind of model of Kaizen. In such a case, important things are knowledge on selection data to be collected, and construction of data collection system, knowledge on selection of analysis method and tools, knowledge and experience, knowledge on selection of evaluation method, and knowledge and experience on decision making and execution of some his or her plan. So these knowledge are not described in the traditional CPPS, but they are main players in the digital triplet. We'd like to describe these engineering cycles as the process knowledge. In other words, we'd like to formalize or collect and archive the process knowledge, support human activities by reusing and deploying the process knowledge and employing the knowledge to education and by generalizing the knowledge. That's what we want to do. In other words, the engineering support we assume is as shown here. We'd like to represent an engineering cycle as a combination of digital twin and process knowledge on digital triplet. And this is, I believe, possible by recording and engineering cycles in the cyber world, including collecting data, which data they collect, which data they focus on, and which tools they used in analyzing data, and so on. So the history is represented as the log in the cyber world. This is the basic fundamental concept of digital triplet. Let me describe the image of digital triplet with an example. This is the example of machining molds for injection molding of plastics. This is a real example, and this company is famous for making high-quality molds. They machine the molds by machining centers, and various know-how are needed in generating NC programs to operate the machining center and selecting cutting conditions and tools. They need know-how in selecting cutting tool conditions and tools. First, on the digital triplet system, we recorded how skilled workers determine the NC program and cutting conditions. For example, we developed a digital twin system of the machining center, and a team of skilled workers makes NC programs and machines a mold with the NC program and certain cutting conditions, and they evaluate the quality of the machined mold and modified NC programs and cutting conditions. And they repeat this cycle until they get the mold with enough quality. In developing the NC program, they pursue high quality of the mold and shorter processing period, and often makes failures as shown in these photos. These dots are the failures. Even experts should repeat such trial and error 2 or 3 times, and the total period of time to finish the mold is 3 months or 6 months. For extracting engineering cycles, I'm sorry, some parts are in Japanese, but for extracting engineering cycles of the mold processing for injection molding, we analyzed the record of processing data the company collected and executed interviews to experts and constructed an engineering cycle model for molding process like this. For describing such process knowledge, we are developing a process modeling language for describing formally. Okay, this is process modeling. We call it process modeling language for digital triplet, or PD3. We utilize IDF0 as a basis. The model of process description consists of problem-solving layer, physical layer, and information layer corresponding to the intelligent activity world, physical world, and the cyber world. In each layer, the process is represented as a sequence or network of actions. Each action has input information. Sorry, I forget to change it. Oh, okay. And an execution of action with some tools and knowledge, and some intention of actions, and output some information. Rationale and annotation are also described. Through this knowledge extraction exercise, we uncovered two findings. First, while the expert executes the latter part of this process starts from here to right side, and the expert executes the latter part of this process with CAM, computer-aided manufacturing software. They do not use this part, use CAD in the CAM. They do not use CAM in the former part of the process. They decide important conditions for processing just in their brain. Second, in this former part of this process, they think the procedure of cutting in the reverse order of the real procedure in the physical world. Namely, they determine the condition of finishing here and here. Then they determine the condition of semi-finishing around here, and finally they determine the conditions of the rough processing around here. This illustrates a part of process description in the problem-solving layer for selecting of finishing tool. First, the expert estimate required length and R, radius of the tool. And if radius is larger than 0.1 millimeter, they try to select a tool from standard tools the company prepares beforehand. Here, the guiding principle is shorter length and larger R is preferable. If the expert cannot find out the tool, they search for special tools which are not used regularly in the company. The guideline here is also shorter length and larger radius is preferable, and deformation should be smaller than 15 micrometer. If they find the tool, this action selection of finishing tool is terminated. If they cannot find the tool, they should use EDM, electric discharging machine, instead of the normal machining. So anyway, the top expert in this company recognized that this engineering cycle model is useful. In this way, we extracted an engineering cycle as a process description. And then, as a second step, we asked knowledge engineer analyze the process data and organize the flow of the mold machining process. And we will find that some parts of the process can be supported or replaced with software tools and AIs. For example, in the example procedure, each action can be supported by CAD, a table, or catalog. Also, these estimation length or radius can be automated by using CAD. In this way, the engineering cycle model becomes smarter, digitalized. As a third step, a novice follows the generated mold machining process to learn the process. As a result, the novice will be able to machine the mold with acceptable quality with the support of the constructed engineering cycle model. We did some experiments of NC programming by novice who can operate CAM but do not know anything about the mold processing. This is the result of the mold process by the novice without engineering cycle model. Problems include cutting direction should fit to that of plastics flow, but this is not. The size of the tool is incorrect. The load on the tool are too much since the number of processes is too small. 5 steps is too small. The top expert in this company judges this process is not acceptable. This is the result with the engineering cycle model. The cutting direction is correct, appropriate tools are selected, and smaller loads on the tools by dividing the processes. It has 9 steps of the process. But the order processing is not good around here, but this can be modified. So by using the engineering cycle model, the novice understand the flow of the processes, the way of thinking to select the conditions of each process. This is our achievement. What we'd like to do with digital triplet, by accumulating engineering cycles on digital triplet system, we can extract tacit, we hope we can extract tacit knowledge, and by using such extracted knowledge, the skilled workers can try to develop new skills. And by repeating these cycles and repeating development of various digital triplet systems, we as a researcher, we can arrive at some design methodologies of digital triplet smart manufacturing systems. This is our goal. Okay, if you don't have any questions, let's move on to the final part. Okay. Sorry, I skipped this slide. There are some research efforts on human-centered cyber-physical system. So digital triplet is something, a combination of human engineers and cyber-physical production system. And digital triplet does not aim to automate manufacturing, rather to support human engineers. And we dare to decompose the cyberspace of CPPS into 2 worlds: digital twin, which models the physical world, and intelligent activity world, where human solves various problems by using the digital twin. And there are some research efforts on human-centered CPPS. In these efforts, I dare to say that human mainly means the workers, but the target of digital triplet is intelligent engineers, and digital triplet aims at providing an environment with supporting functions where engineers construct engineering cycles on their own initiatives. This is the new type, digital type of continuous improvement, so to speak. Okay, do you have any questions or comments? Okay, fine. So then let's move on to the final part, learning factories. You may have already known, but this is the concept of learning factory. It's a trend, I think, especially in Germany, to construct factories in universities for the purpose of education and research. So if we have a factory in a university, it is very easy to teach manufacturing system. Their active experimentation and concrete experience reflect observation and abstract conceptualization. So we can run this kind of cycles on manufacturing systems. And according to the concept of learning factory, we have constructed a much smaller factory than this very big one. It's at the TU Darmstadt. Okay, this is the overview of our learning factory named Digital Triplet Type Learning Factory at Race, or D3LF at Race. Okay, the learning factory we developed is used for education and research from the viewpoint of manufacturing system. And rather than machine tool or processing and related engineering activities, including design, operation, maintenance, or continuous improvement of manufacturing systems. And including lectures and practice for undergraduates and graduates. For education, we believe digital triplet, especially recording engineering processes, is very effective because it can record the processes executing tasks by student. By watching the model, students can review what they did and how they did. And by comparing their record with the expert processes, they can learn a lot where is good and where is not good. And we also do research, of course, for example, developing a method to support engineers in executing continuous improvement by using digital twin. Utilizing digital twin and, of course, digital triplet is the key. We break down the objective into requirements for the D3LF at Race. This figure illustrates the overview of the D3LF at Race. It consists of an automated assembly line as the factory part in the physical world. Digital twin consists of physical world and cyber world. And engineering process description subsystem implements the implement the intelligent activity worlds so far at the start point. The requirement for the factory part can be summarized as follows. The factory should be automated as much as possible because we think this is an image of Industry 4.0. The claim of digital triplet includes that even if the factory is automated, manufacturing system engineers are indispensable, and they are the key to realize continuous improvement of CPPS. The user can execute, second specification is that the user can execute problem solving, including continuous improvement with the factory. For realizing the first requirement, we constructed an automated or assembly line of Lego cars as shown here. The video, I will show you the video. The video shows the assembly process of Lego cars, but the speed of the video is 2 times faster than the real one. Let me see. Oh. Okay. Oh, sorry. This has no sound. It's okay. First, also tire is put, and second, it's some body assembled with the robot. On the third stage, the roof is assembled and the quality is checked with the slope behind the robot. You can see, yes, this is the slope, and confirms the car car is running, and if the state the product is normal, and the robot put the car in this box. This is a very rough process. Oh, I made a mistake. Sorry. How can I do that? Okay. Sorry. Just a moment. Please be patient. Let's do it again. Okay, I'll come back. Sorry. And for the second requirement, we installed education mode into the line, which stops the line or decrease the speed of the line. Also, we design the line so that the user can arbitrarily change the behavior of the line by changing the programs of controllers installed in the line. Actually, the line has 2 robot controllers, 3 programmable logic controllers or PLC, and 12 actuator controllers. This slide shows the list of the education mode. For example, if the first education mode is activated, stoppage of the line because of position error of the base assembly at stage 1. This is the I have to show you a video. Okay, this is the normal mode. Tire is body is but now, okay, as you see, I'm sorry, this is not fast education mode. But anyway, here the robot failed to pick up the body, and then it failed to assemble the body here. This is one educational mode. And what we are doing is, okay, so let's move on to the second part, digital twin. The requirement for the digital twin, the system should be equipped with the digital twin that models the physical world, since the digital twin is a prerequisite for digital triplet. The digital twin should collect operational data of the assembly line as much as possible, and digital twin should model the assembly line as much as possible. Okay, as shown here, we constructed digital twin with 2 main functions. First, we developed a log data here, log data base for realizing this requirement. Okay, the second requirement. And we employ a 3D model-based simulation for visualizing the behavior of the line for the third requirement. We designed digital twin to be expandable by adding, of course, various software. This movie shows our online simulation of the digital, the 3D simulation system. Here, this 3D model moves in a synchronized manner. Okay, I'll show you. Okay, like this, synchronized manner by receiving the signal from the real controllers in the physical world. Okay, okay, the simulator receives the real data in the physical world and moves synchronized manner. Honestly speaking, it is very hard to make such online simulation, and this is still under development. Okay, in terms of the requirements for digital triplet, first the system. Oh, sorry, time is running out. Okay, sorry. The system should support knowledge engineering, recording, engineering processes executed by manufacturing system engineers. And anyway, we developed engine process description subsystem using the PD3 language, and it consists of PD3 description editor for supporting describing engine cycles, and rule checker to verifying the correctness of grammar of the description, and referring setting tools that links for actions in the intelligent activity world to the operation in the physical and cyber worlds. And we executed some experiments to experts using this learning factory to collect examples of engineering processes like this. Sorry, it is in Japanese, but expert is the other side of the online system, and they asked to check the condition of the machine. So we recorded how they find out activated failure mode, and how they find out some solutions against it. And we recorded the process like this. It's very complicated, but it consists of intelligent activity world and physical world and cyber world. So we succeeded in describing the engineering cycles executed by the expert engineers in the experiment using the system. We will try to reuse such descriptions by using the model. So let me summarize quickly and discuss some points. So there were a lot of research efforts on formalizing tacit knowledge, representing expert tacit knowledge on computers historically. But I think they were not successful. I believe one of the causes is so-called symbol grounding problem. In other words, we can model knowledge, process, and know-how in a computer mainly by text and symbols, but true meaning of those texts and symbols cannot be represented in a computer. Digital triplet represents the meaning of text and symbols by mapping them to the data operations in software in the cyber world. We believe that combination of symbols and data is a hopeful approach, and the combination of process knowledge and functional knowledge is also a hopeful approach. We derived some observations from this experiment and some exercise by the student. Inconsistency between cyber world and physical world is very critical, especially inaccuracy. And models and simulators are not enough. They can only represent some phenomena they can model. Actually, honestly speaking, expert engineers in the experiment did not use digital twin enough. It is difficult to extract meaningful data from huge amount of collected data, raw data. So it is critical to choose appropriate data to collect and model simulations to use for constructing engineering cycles. Now we are just beginning at the beginning stage of digital triplet research, and we are running various digital triplet projects as listed here, but I don't skip. I will say skip it. And this research is financially supported by Japanese founding agency or ministry, METI, and some JSPS grant and some industries. Thank you very much for your attention. I'm sorry, my presentation was too long than expected.
Yes, but it is, I think, because the time it should be more. Any questions are there? You can be put now. I hope the mics are open.
Basically, do you understand my talk, or is it very difficult, or my English is too poor to understand?
I think it is good, but maybe the digital triplet concept and the missing or hidden problem which has come to that could be heavy. We have Ishan Kaushal.
Yeah, hello.
Yeah, Mr. Ishan, please.
Yeah. So nice talk. I would like to ask a question.
Yes.
So can we say that intelligent activity world is a knowledge base which we create through the domain expertise?
It's a very good question. Yes, knowledge. How can I say? Let me see. There might be some architecture. Okay, knowledge base itself. So, in my view, okay, in my view, knowledge base is between the intelligent activity world and the cyber world, so to speak. And knowledge activity world is something, field or environment where human engineers works by using digital twin or physical, the object in the physical world, various software in the cyber world, including knowledge. Okay, so human uses knowledge base in the intelligent activity world. This is my idea of intelligent activity world.
Okay. Yeah. Thank you. And just a comment that yeah. So bringing domain expert into the loop seems like a good idea, because in AI also people are talking about moving from model centric AI to data centric AI, where domain expertise can really help in labeling data, and that can help in increasing the accuracy of machine learning algorithms.
Yeah.
So seems like a really good idea.
Oh, thank you very much.
Thank you.
Yes, I think I agree with that. Yeah, that's a trend. Yeah.
And does PD3 and D3 similar to the business process modeling and notation language?
Yeah.
Okay.
Yeah, language itself is very similar, but we'd like to where is the correct slide? But we'd like to link. We'd like to add a lot of links from the symbols to the operation data or operations of software. So this is something like RPA, robot process automation.
Okay. Yeah, because we have worked using BPMN to process and link data and orchestrate the whole data and physical interactions happening. And this seemed similar to that.
Yeah.
Except that the tacit knowledge and the wisdom, which is beyond simple knowledge that one acquires, also acts when the seniors engineers are at the station observing it. So we understand the importance of digital triplet now.
Oh, thank you very much.
If there are no further questions, I may seek permission from Professor Yasushi Umeda-san to close the session and with the great thanks that he made time for this session, and also those serious Industry 4.0 followers who attended this session. I am very, very thankful to you. Thank you, one and all. Thank you.
Thank you very much. I'm really sorry that my lecture is too long.
No, it's correct. Exactly 5 p.m. 3:30 we have started. 5 p.m. we have ended. Perfect timing.
Okay. Okay. I really enjoyed this lecture. Thank you.
Thank you.